Hello, everyone, and welcome back. I would like to welcome to our ML conference stage Nitin Sharma, who is a senior research scientist with PayPal Risk Sciences. Go ahead, Nitin.
Hello, good morning, everyone, and welcome to this presentation on reinforcement learning-based meta-learning applications for fraud detection. And the idea here is we are going to introduce, just a second. It seems like I'm getting double signed here.
If you have your phone on, you may be getting a feedback sound. If you have your computer audio running, you may get a feedback. Through loud and clear to the audience.
Got it. So maybe I'll try this one more time. So hello again, good morning everyone, and welcome to this presentation on reinforcement learning-based meta-learning applications for fraud detection. Today we're going to talk about the applications of reinforcement learning, specifically in PayPal domain, where we see a problem of temporal model decay that happens because of concept drift and changes in the distribution of the data. And we're also going to see the issues that arise because of a deferred source of truth. When I say deferred source of truth, what I mean here is essentially the source of truth on which we actually perform training of the model is available at a lagged instance in time. And to solve these two problems, we introduce a formulation in reinforcement learning. So my name is Nitin Sharma, and I work at PayPal's AI research team as a senior research scientist. And most of the work that we do here is related to payments fraud detection, but we are also looking at applying state-of-the-art AI and ML methods for domains such as credit, marketing, and also related to domains such as different kinds of fraud MOs. So credit domain actually surfaces various kinds of problems. And on the fraud side, we actually have problems that could be related to account takeover, ACH fraud, credit card fraud, and so on. So today's presentation is divided basically into this kind of agenda. So first, we start out with the problem background and motivation. So we'll talk about the problem of fraud detection and also the issue of diversity of fraud patterns. We'll also talk about reinforcement learning as a general concept, and then introduce the idea of model-free RL, but also look at Q-learning and trust region policy optimization as two methods that we've used for this problem formulation. We will cover two different use cases in this problem. The very first use case is a sequence to label learning use case. We use a double Q-learning or Q-learning approach in this specific method. And the second application is a semi-IID learning approach, where we use meta-learning and trust region policy optimization approaches. And lastly, we'll conclude this presentation with some conclusions. So why do we care so much about reinforcement learning or meta-learning applications in a system like PayPal? So look, if considering PayPal as an e-commerce transaction processor, which has over 350 million customers, we actually entertain a heterogeneous large volume payment ecosystem. So this ecosystem involves people from all over the world. Sometimes these are just single users, just users that are just transacting with each other, or these could also be businesses that are sending money and receiving money to each other. And this transaction happens in multiple currencies, and it happens with multiple purposes too. So like I said, it could be money transfer, it could be purchase of goods that are digital or tangible, or it could simply be services. And these transactions could be cross-border transactions, but they could also be domestic transactions. They could be local or small scale, but also retail and large scale transactions. The other aspect that poses complexity to it is, while some of these transactions are based online, we have some transactions that are conducted point of sale or in store. And due to all of these variations, we find that the ecosystem is highly heterogeneous, and it's a dense mixture multivariate distribution when it posits itself from all of these variations. The criteria is also multi-objective. So while we want to be able to reject fraudsters as quickly as possible, we also want to be able to approve good users also as quickly as possible to have a good customer service experience. So it's a criteria that we have to balance while being able to be precise in fraud detection, but also at the same time cover good users as accurately as possible. And it is also a diverse and temporally evolving ecosystem of fraud patterns, because fraud patterns evolve significantly across different geographies. And as the technology evolves, we also see different kinds of fraud patterns emerge. There's also severe class imbalance because you find a small percentage of transactions are fraudulent. So it is kind of like looking for that needle in the haystack. So in some sense, you have a class imbalance that posits itself from these domains. And then we also have a delayed availability or source of truth. So what we mean there is when fraud occurs, we don't really have that piece of information immediately. It's always deferred by a few weeks because that source of truth comes back to us based on feedback that we get from customers, or based on feedback we might get from issuers and merchants that might be using PayPal as a payment service provider. There's also a lot of domain-centric knowledge and strategy and complex segmentation that leads to large feature engineering. And sometimes this feature engineering can pose problems such as high correlation, because you might be doing this in an unsupervised context. And when you apply it to a more supervised context, you might see that there could be some redundancy in the feature space. To just give you a very quick sense of scale here. So there are about 377 million accounts. This is a 2020 statistic, just to give you a sense of the scale that we have. But also broadly, a point to focus here is 15.4 billion transactions. And so we are looking at 30 to 40 million transactions per day. And all of this payment volume actually occurs in multiple countries, in different currencies and different funding instruments as well. So certainly a very complex ecosystem of transactions happening all over. Now, in terms of the kind of fraud patterns that happen at PayPal, just to give you a very quick sense of it, since we've looked at scale and we've also looked at some of the motivations that come from the heterogeneous ecosystem. We first of all have stolen identity type of fraud, which actually simply occurs when a fraudster gains unauthorized access to a given wallet or to a given account, to a given PayPal account. We could also have stolen financials, where you could have a stolen instrument such as a credit card or a bank account that is stolen by a fraudster, and then a fake PayPal account could be created to leverage those stolen instruments. We also have other kinds of fraud patterns that could evolve in the ACH domain, such as lack of sufficiency of funds. This also happens because bank transfers can typically take some time. And during this time, we may not have upfront information on what's the latest account balance of the transacting customer. And so it's possible that at the time of transaction, the customer doesn't have enough money to actually support the transaction that they're trying to make. We also have collusion fraud, where potentially buyers and sellers could collude with each other to actually cause fraudulent patterns. We also have fraud on the credit side, and this fraud actually emerges from applications that customers could make, and a lot of vetting process is then involved in order to assess whether that transaction is, or whether that credit application is likely going to go delinquent over time. So also we see that there is complexity in terms of the e-commerce volume, but also the kinds of fraud patterns can actually be different depending on the kind of fraudster. But also many times these fraud patterns occur simultaneously and in some sense in an overlapping manner. So something for us to also consider. If there are fraud patterns that are layered, for example, you had somebody whose identity got stolen, and then the fraudster also leveraged a stolen financial on top of the stolen identity fraud, then now you see a layered proposition. And so one of the issues that could arise is, how do you label this transaction? Would it be a stolen identity transaction or a stolen financial transaction, or could you use this as a multi-label formulation? So a lot of these challenges then make risk assessment in such an ecosystem fairly complex. With this, we're going to make a segue into reinforcement learning and the ideas related to reinforcement learning that are applicable to these two problems. First, how do we ensure that temporality that causes models to deteriorate can be countered effectively? And second, how do we ensure that the source of truth that usually arrives in a deferred sense, how do we ensure that that is available upfront and ahead of time, or in an accurate manner, so as to develop maybe a tag learning system? And so we'll discuss these two facets as we go on. So a quick overview on the reinforcement learning side of things. So the core idea in RL actually involves an agent and environment. The agent basically just acts on the environment, and the dynamics of the environments are largely unknown to the agent. And the environment's reactions to the interactions that the agent makes are then defined by the model of the environment. Also, we sense that the agents can be in different states, and they can perform different actions depending on the feedback or the reward. And the transition of the agents then occurs from one state to another. And the probability of transitioning from one state to another, which is typically known as the transitional function, is something that's under consideration even in the fraud detection domain. The environment also rewards the agent from a set of rewards and penalizes the agent from, again, a set of penalties, depending on whether the action was productive or counterproductive. And finally, also the strategy by which the agent takes an action is effectively termed as policy. Because the domain of RL is pretty broad, I wanted to very quickly provide some sort of an overview on the agent environment synergy and how this can be actually used to actually formulate problems in different ways. So the very first kind of problem formulation that we've considered is the model-based RL, where the agent is familiar with the model of the environment and learns about it through interactions with the environment. The other form of RL that we see is model-free, where the agent is actually trying to learn the strategy to interact without explicit knowledge of the model of the environment. Now here, one of the things to note is the goal of the agent is basically to maximize a certain value function, and it is to actually predict the expected number of future rewards it can receive in a state by acting on the corresponding value, and also to quantify how good a given state is. So value function is a good measure of that. Now, in all the categorizations that you see to the right side in model-free and model-based RL, we covered one method in policy optimization, which was the trust region policy optimization, or TRPO. And the other case study, which is the semi-IID case study, is based on TRPO. And then we have a study which is sequence to label study, which we will demonstrate the Q learning or the double Q learning approach for. So here we are explicitly solving a sequence to label learning problem. Now, not to get into too much detail, but because the study that we tried for Q learning and double Q learning and TRPO involved some optimization parameters, I wanted to give a very quick sense of the key model components here in the RL terminology, and then also translate for you what each of those mean in the fraud detection domain. So here, generally in the RL terminology, you have a sequence of interactions that happen between the agent and environment, and this is a single sequence here is either an episode or a trajectory. In the case of the fraud detection domain, the sequence of interactions is essentially a series of transactions that happen from one or more accounts. So you could have an account, or you could have an IP address, and there could be a sequence of transactions or payment attempts or login attempts that could occur, and this sequence will be termed as an episode. Now, each episode in the RL context comprises of states, actions, and rewards at any point. Another way also we often see in RL context is to categorize things as either on policy or off policy. So in on policy, we are typically using deterministic outcomes or samples from a target policy in order to train an algorithm. And in the off policy domain, we are training basically on a distribution of transitions or episodes produced by some kind of behavior policy. So in our case, we have actually demonstrated application of on and off policies both in different flavors, and we'll actually talk about that more as the presentation progresses. And then lastly, we also have the transition function and the reward function. We will also see in the forthcoming slides as to how this reward function is optimized and tweaked more specifically for the fraud detection patterns, where you might care more about declining a fraudster who tries to commit high dollar value fraud with more efficacy and accuracy. as compared to maybe a low dollar value transaction. So in that sense, we could tweak the reward function as such, and we'll demonstrate that too. So let's move to the next slide here. So now, in general, without dwelling too much into the mathematical details here, we can quickly identify three different aspects that we'll also be covering in the case study. The first is the transition function, which simply records the probability of transitioning from a state S to state S prime after obtaining reward. And then you have the state transition function itself. And then you have the reward function R, which actually predicts the next reward triggered by a given action. As I mentioned earlier, the policies themselves could be either deterministic or stochastic, depending on the action that's taken. Just to very quickly elaborate on that, the policy can be deterministic for every state that there is a single action for, and that is defined by the agent. And then the policy actually, in this case, there could be instances where the policy actually returns a probability of taking a specific action for all possible states in a state or in a set of states S. So also it is important for us in the convergence trajectory here to assess how good is the state of the agent that the agent is currently in, and also to be able to assess the value function. And it's also to be understood that every state, and we'll see this in the fraud detection context, there is a value function that determines the total reward that can be obtained. Lastly, also want to emphasize basically an important aspect of discounting factor, gamma, which in this context also penalizes the rewards in the future. So in general, this is also because when you look at future rewards, they may have higher uncertainty, and they may not necessarily provide immediate benefits. And then also this kind of discounting will provide some kind of mathematical convenience. So we don't really need to track all the future steps, and we don't need to do them since epoch or since the starting point of the convergence trajectory in order to compute a return. This is important because in a lot of sense in the fraud detection domain, we might be going back to 5 to 6 years of data. And so discounting factors help us in a way that we can aggregate penalties over short temporalities, and in that sense we don't have to keep tracking them forever in order to compute returns. Lastly, we have 4 different functions that are 4 different propositions again. So the very first one is the state value. All of us, the ones who are familiar with reinforcement learning would recognize this as something that's just an expected return that can be obtained when we are in a state S at time t. Now, similar to the state value, we also have this notion of Q value, and this becomes important because the method that we are trying to use is Q learning. So similar to the state value, the action value notion actually is simply the expected return that is obtained by taking a specific action at a certain state and for time at a certain time t, which is effectively this Q value is also called as the action value. Now, there are also different ways in which you could determine one from the other. So the action value can be determined from the state value by simply taking the action value over all possible actions in a state, and then multiplying that by simply the probability of that action in that state. Lastly, we have also the advantage function, which we will use repeatedly in the Q learning formulation. And this is simply telling you the difference between the Q value for an action A in state S and the value of the state S. So it just simply tells you, if you were to take an action to move from your current state to a new state, how much better that new state is expected to be in terms of the advantage function. And we use this repeatedly as a criteria to keep measuring whether the algorithm is converging or not. Lastly, just to very quickly emphasize here, we have the Q learning or the quality learning formulation. This is just using the temporal difference update or TD rule, the temporal difference rule or the TD update rule. And the idea here is to just simply keep applying the TD update rule by keeping a certain learning rate and then assessing the reward and the discount here. So not to go too much in detail, but this is one of the off-policy reinforcement learning algorithms that we have used in this formulation. Lastly, just to present some very quick ideas on the trust region policy optimization. So here we use very largely the the minorized maximization algorithm. We actually determine the trust region here very broadly as a concept of trying to determine what should be the maximum step size that we want to explore. In the minorized maximization algorithm, the key question that we are simply trying to pose here is, when we do a policy update, can we in some sense get some kind of performance or convergence guarantee that policy update will always result into improved expected rewards. And lastly, we have the importance sampling, the idea of importance sampling, where we simply want to keep rewriting the objective function so we can keep using samples from an old policy to calculate the policy gradient. Now, in the fraud detection context, as there is temporality, it's possible that a policy could have worked out very well for us, let's say in the first or the second quarter of the year. And then we want to maybe bring back samples from that policy in order to compute the policy gradient. So we use importance sampling in a temporal manner. Now, just to very specifically emphasize on the study itself. So our study actually involved a paper by Zinin Vera and Feng. The citations of this are available in the references section. The problem that we are simply trying to pose is, given that you have a sequence of transactions from the past, can you determine whether a new transaction is legitimate or fraudulent? Now, in this case, the challenges also again are temporality, heterogeneity, and class imbalance. So in that sense, we are also trying to divide this deep RL method into three different parts. First is the instance selection, where the example is chosen according to a policy function. And then the selected examples are used to train a better relational classifier. Lastly, you have the instance selector that updates these parameters with a reward which is computed from the relational classifier. So this is very broadly the idea around sequential learning using Q-learning. The variation that we apply in the fraud detection context is use double Q-learning. So let's dive a little deeper into the data description and then the neural network architecture. So the data that we used for this study was the stolen financial data, which was related to the credit or the debit card domain. It was in the 6 months time frame. It was hallmarked by class imbalance. We actually transformed the original feature space, which was about 625 features, close to about 2.5 million examples. And first, we conducted a principal component analysis on top of this data and developed 78 principal components. We also used two variables that were untransformed, which was time and dollar value. The time stamp here is important because this is, again, a temporal difference update rule, and we are taking temporality into consideration. So the time here is the time that is elapsed between each transaction and the first transaction that appeared in the sequence. So we have this relative delta applicable for every element of this tuple. Lastly, we also look at monetary value in the raw form. It has several outliers because you could have money per transaction having a skew. Typically, it is a positively skewed distribution. And then we computed several performance measures, mostly AU, PRC, area under the precision recall curve, and the receiver operating characteristic curve, which was dollar weighted. As I mentioned, it's important for us to catch high dollar value fraud with greater accuracy. So now to go into the details of the architecture. The architecture was a three-phased neural network architecture. It's basically an intelligence system that tries to detect fraudulent transactions first with an autoencoder. The autoencoder, the input to the autoencoder are the 78 features that we had in the previous phase. This is tuned with a definitive metric. It's a hyperparameter tuned with a definitive metric and based on the performance of the next operative network. So what we're also doing here is the next operative network, which is a classifier, actually feeds input or helps us tune the autoencoder better. So it's in some sense, it is a supervised framework that we try to conditionally learn the distribution of the features, conditioned upon the fact that it could be a fraudulent transaction or a non-fraudulent transaction. Followed by the autoencoder, we have the mediator network. The input to the mediator network is provided by the hidden layer of the autoencoder. The output of the mediator network is simply a softmax with two nodes, either the fraudulent, basically just to predict whether this transaction is fraudulent or not. And the performance measure that we use here is the precision recall curve. Now, so these are the two parts of the phase system. The third part of the system is really where we bring in reinforcement learning. So here the idea is to design an intelligent system that learns to detect fraudulent transactions efficiently using this cascade. Now with the Q-learning here, we have an activation function, which is learning a sigmoid with a deep Q-learning algorithm. So here the agent basically receives rewards depending on the accuracy of classification. It could be a positive reward if the transaction is correctly identified, more so if it is of high dollar, otherwise it's a negative reward. And then the method is also characterized by heavy class imbalance. We have a 5-tuple framework. So in this case, we have the state that is being defined by input x1 being in the initial state s1. So this we actually try to determine whether the transaction is fraudulent or not. And then the next state in the transition is defined given the hidden layer of the neural network. So again, you have multiple actions that the agent takes depending given by the dataset label, whether to decline or approve the transaction. And then you have the transition probability, which simply moves from, the agent simply moves from one state to another, approve to decline, depending on, also depending on the order in which the data was actually read. To quickly emphasize on the reward, so like I mentioned earlier, it is important for us to decline fraud transactions of high dollar value with more accuracy. And then we try to balance this using a second level learning, which reduces the decline on good users. But as you will see in this formulation, the reward is actually +1 or -1 if there is an accurate or inaccurate classification of the fraudulent transaction. And the reward is positive delta or negative delta if it is misclassification or classification or correct classification or misclassification of a good transaction. And lambda here actually simply is a value in the interval between 0 and 1. So less penalty if it is a good transaction, greater penalty if it's a fraudulent transaction, correctly or incorrectly classified. So basically just some information on the parameters here. Basically, this just gives us information around how the intelligent system was designed. It's an imbalanced classification Markov decisioning process. And then here in this case, we have a terminal E, which just simply defines when does the episode end and then what happens when the episode ends. And lastly, we have a policy, which is simply a mapping function between the states and the actions. The final values of the parameter search here are specified here. We actually did a parameter tuning on lambda and then memory replay, which was around, in this case, it was around 400,000. And that is that many sequences. And then the gamma value was 0.96. So these are parameters that were used for the Q-learning approach. So basically, the algorithmic process is divided largely into 3 different algorithms. First, you have the QCCFD approach, the train agent, and the environment simulation. The idea here simply is to recognize that the transaction space is completely read for all the transitions or for all the transactions in space. Here we have about close to about 300,000 transactions. And then you have the feature space that goes from V1 all the way up to V28. So you read the data, you normalize the data, and then you randomly initialize the weights on the thetas, and then basically train all of these 3 networks in a sequence. You do autoencoder training, mediator training, and then the agent training. So just to actually very quickly cover the performance and curves here, or performance analysis here. So we actually trained this model with a Q-learner with the original tag, and also the double Q-learner with tag variation. So with the original tag, this was the deferred source of truth with plain Q-learner. And the ratios that you see are the ratios of performance of the Q-learner over the current champion. So we have current champions without RL, just running refresh. So basically, we have models that are simply taking into consideration new data and just refreshing the model performance. So we are comparing the increment in performance we get from the Q-learner relative to the baseline. And so the ratios above 1 actually indicate that the Q-learner is doing better than the current champion or baseline. Now, the double Q-learner with tag variation is where we provided a deferred source of truth. So here we did not have the original tag. We actually use RL formulation to predict the source of truth ahead of time at the time the transaction is happening. And we'll discuss some of the details here in the next slide. But bottom line is we received better performance there. And then lastly, we also were able to improve tag accuracy a point in time with double Q-learner and tag variation being higher when we actually had point-in-time tag definitions that were compared. We also were able to use this architecture for rectifying mistagging. So as I identified earlier, sometimes you also have one transaction that could be mislabeled as another. And so if you have this source of mistagging, or if you have the original mistagging information available, you could provide that to the RL context ahead of time, so it starts to act as a tag learner while also rectifying these tagging inconsistencies. Lastly, also want to talk a little bit about the meta-learning case study, the second case study where we had the TRPO variation. So the idea here, basically, as I mentioned earlier, was at inferencing time, we don't have the source of truth. But again, from the point of view of feedback loop, can we make that source of truth available ahead of time? So here we tried a variation of TRPO with model agnostic meta-learning algorithm, or also known as MAML. And with the variation of TRPO and MAML, we were trying to assess if the tagging inaccuracy can be mitigated and the source of truth can be available ahead of time. So as we can see here, with incremental tag refresh, we see an accuracy boost up of about 1.09x. And then the same network framework was applied for rapid refresh. So we had the reinforcement learner deployed in a setting where we had an auto refresh happening at different points in time based on change point detection methods that actually tagged whether the RL formulation or RL algorithm should kick in order to refresh the model or not. And we tried this consistently over a 6-month period, and we see 1.15x lift, incremental lift over model, which are just refreshed periodically, let's say at a 3 to 4 week period. There was, in this particular iteration, we didn't try architecture update, but with architecture update and cost function updates, we saw a 1.2x lift approximately. Lastly, to quickly establish some conclusions, we see that reinforcement learning methods mitigate against model deteriorations. We also see that these meta-learning frameworks actually improve tagging accuracy and also allow us to advance the availability of source of truth, which can be used then to train your models on more data, more recent data even. And then the variations of Q-learning and TRPO, we see aid better in fraud detection capability. We actually did utilize a lot of GPU infrastructure for training these approaches, which were trained on, as I mentioned, billions of events eventually in the pre-production setting over 4 to 5 years of data. So with that, I'm concluding this presentation, but I'm happy to take any of your questions.
Thank you, Nitin. If you want to unshare your computer, you'll be able to see any of the chat that comes through. Currently, we don't have any questions in the queue for you, but I encourage the audience to address any questions to Nitin as the day goes along, and he will be monitoring the chat and address those directly. I'll give it another minute here just in case thoughts come through from our audience. I think we're good. So Nitin, if you want to unshare your screen, and we will take a quick break, and I will prepare Harpreet to come to the broadcast stage. Thank you so much, Nitin, for your great content.